Yeah, so thanks for having me. It has been a pleasure to attend some of the talks given this week so far, and hopefully there are going to be many other interesting talks throughout this afternoon. So I guess I should apologize a little bit because the title of my talk is a little bit misleading. Somehow I'm mostly going to talk about Cauchy completions of two categories, and then I'm just going to kind of apply it to this this case of multifusion categories and finite semisimple two categories. But somehow the focus is rather on a categorification of the notion of Cauchy completion. But before actually doing this, talking about this kind of scary operation, I just wanted to, recall some very basic facts about like ordinary Cauchy completion of like linear one categories. So the perhaps most fundamental, you might even want to say trivial example, is the one where you start with the full like subcategory on the one-dimensional vector space. And then kind of, as you know, when you do like linear algebra, you kind of quickly realize that like only having a one-dimensional vector space is not very interesting. So what do? Well, you just end up having to take direct sums of it. And somehow this is made precise by this statement that somehow the inclusion of the full subcategory on the one-dimensional vector space into the category of all finite dimensional vector spaces is somehow like a direct sum completion. It's like somehow the only thing you need to add is just direct sums, and then you get everything. And then a little bit more interestingly, kind of when you move on and then you do like representation theory of finite groups, there is something similar happening with the inclusion of the one object category on the regular representation into the category of all finite dimensional representations of your group, at least provided your characteristic is 0 or something like this. But it's also a little bit more complicated, right? Because you not only need to add direct sums, but somehow you also kind of want to be able to take summons of the regular representation, because as you probably all know, right, every finite dimensional reduced representation of a finite group is a direct summand of the regular representation. And so kind of the categorical way of saying this is that you need to be able to split idempotence, because a direct summand of the regular representation defines an idempotent, and if you can just split it, then you can recover your irreducible representations, and then via direct sums you can get everything else. So these two inclusions, right, are examples of Cauchy completions, and in the sense of this definition, where I mean it's equivalent to the usual definition, might be phrased in a bit more, I guess, universal way than what like people usually present. But like somehow, I just want to say that the Cauchy completion for like your favorite linear one category C is somehow the universal functor out of C to an idempotent complete and direct sum complete linear one category. So so I guess the Cauchy completion for me is going to be like both the functor and the category somehow. In this talk, I'm mostly going to talk about the category associated to it, but like the functor is also important somehow. And then it's kind of a well-known thing that the Cauchy completion actually always exists, and kind of unsurprisingly, because there are kind of two parts in the definition, there are actually two parts in the proof, so you can kind of split it into like proving that you have like a universal way of adding direct sums to your categories, and that you also have a universal way of like splitting idempotence in a given category. Adding direct sums is not really difficult, so you can consider this thing that is sometimes called MATC, which is just the category of whose objects are finite sequences of objects in C, and then one morphisms are going to be given by matrices of one morphisms in C, and somehow you can just check that like if you concatenate two sequences, you get like a direct sum for two sequences, right? Well, and I guess for this part, like importantly, you need to have a linear category because you need to have zeros. What's a little bit more interesting is this second part where you want to construct a universal idempotent completion. And for this, you need to consider this category, which is usually called the Karoubi envelope of a category, which is given by the whose objects are given by idempotents in the category you start with, and then somehow when morphisms in C that are compatible with the idempotents. And then you can check that this is, idempotent complete, that you can split every idempotent. Great. And now that I've recalled a bit like the one categorical situation, I want to move on to the two categorical situation. And throughout, I'm just going to want to be working inside a fixed linear two category. And I'm going to make this small assumption that the home categories are actually Cauchy complete, meaning that they have direct sums and you can split idempotents. I mean, it's a little bit of a technical thing. It won't really, I will lecture a little bit, but somehow it's a bit of a technical thing. You don't technically really need to do it. You could just, take the previous Cauchy completion, which is described and apply it to the home categories of any linear category to produce something like this. So it's not a big deal. It's really just a convenient assumption to have. Okay, and unsurprisingly, right, I want to define a Cauchy completion for linear two categories. So it's going to have two steps. One, which is categorifying the notion of a direct sum, and somehow this is just the easy part. So I've bothered writing down a definition, but I'm not really going to bother reading it out loud. Somehow it's the thing you would write down if you had to write down such a definition. I guess maybe the only thing I want to point out is that somehow we actually are using the fact that we have direct sums inside our home categories for this last condition on two isomorphisms. But in any case, somehow this is, I guess, a rather mundane definition, and it's not particularly interesting. I nonetheless wanted to give you an example, which is the so-called two category of two vector spaces. And even though the name might be a little bit scary, it's actually relatively easy to describe. So it's just the two category whose objects are like the category of finite dimensional vector spaces. It's actually take a finite number of Cartesian products of it with itself. And that gives you all the objects, and then the functors are like linear functors and so on. And this has really direct sums. I mean, basically by definition, I just kind of define the objects in such a way that it's somehow clear that this has direct sums. And somehow this is entirely analogous to the category of vector spaces where you just have one thing and just add direct sums. That's really the same thing, but instead of starting with a one-dimensional vector space, you kind of start with a one-dimensional category. That doesn't mean anything precisely, but it's just kind of the intuition behind it. Now onto the actual interesting definition. So I want to tell you a little bit about categorification of the notion of an idempotent, but somehow it's a little bit easier to, I guess, to first try to categorify the notion of a split surjection, which will then naturally lead us to a categorification of a notion of an idempotent. So this was done by a number of people. I guess I should apologize for the name. I didn't choose it. It came out of physics type things somehow, and that's why it's called a two condensation, but it's really a two split surjection or something like this. And what is it going to consist of? Well, a two condensation inside your favorite two category. So it consists of two objects, right? I mean, something you want to surject onto and something that's going to include inside the other thing. So that's my X and Y. And then two one morphisms that go in one way and the other. And then the interesting bit, so I'm going to put some two morphisms onto this. And I'm going to put a gamma and a phi that go from the identity on Y into this composite of F and G. And then these things have to satisfy one condition, which is that gamma has to be a section of phi. And you might just probably wonder, why is that a categorification of the notion of a split surjection? Well, to really convince yourself, I think it's best to play with the notion a little bit, but the very obvious thing to say is that somehow this structure that you can see right now that lives at the top level of this construction actually is a split surjection, right? I mean, gamma is a section of phi, so that is a split surjection. And somehow this is the most straightforward way of saying seeing that this actually generalize the notion of a split surjection. And I guess I can also say that somehow, because this condition is completely like functorial, like these objects are actually preserved by any two functor and things like that, so you can really see that they kind of do behave like split surjections. And so now, if we restrict somehow these types of objects and only look at the structure that lives on X alone, which is what you would do if you wanted to like recover the notion of an idempotent from that of a split surjection, right? You forget that you have something to surject onto. You only have the big thing, and you only look at what lives on the big thing, which in this case is X. Well, we will get our categorified notion, and it's very inappropriately called a two-condensation monad, even though it's not a monad. Again, I didn't choose the name. You can go complain to Theo Johnson Fred if you're upset by the fact that it's not a monad. But in any case, a two-condensation monad is going to be on some object X of C is going to be a one morphism E together with two morphisms, mu and delta. So mu should be thought of as some kind of multiplication and delta as some type of co-multiplication. And then mu has to be associative, delta has to be co-associative. Those are very standard assumptions. And then you also want the Frobenius relations to hold, which mean that delta is a bimodule one morphism, where I view E as a bimodule using the multiplication mu. So that this gives you like two relations, which are, I mean, typically called Frobenius relations in algebra and topology. And now, I mean, mimicking the usual definitions, I can just, say that a two-condensation monad splits if it can be extended to a two-condensation. So that's really, again, like I'm just splitting an idempotent, but now my idempotent somehow lives in a two category as opposed to a one category. The only example that's really easy to talk about is that of two condensations monad in two vect that live on vect, so that's very specific. But if you unfold the definition, somehow what you end up getting is basically the notion of a separable algebra in like in your favorite category of finite dimensional vector spaces. I guess here I'm lying a little bit because I said two condensation monads are not monads, and now suddenly things have units. Somehow it's because this category is nice enough that you can actually put units on everything and you get the same thing in the end, but it's not true in general. And then you can also somewhat easily convince yourself that every two condensation monad actually splits from this separable algebra picture, because a separable algebra, at least if your field is the field of complex numbers or something nice enough like that, because separable algebras are just given by direct sums of matrix algebras, and then a matrix algebra which is split to one copy of vect. So that's how this goes, and then you can somehow, categorify the notion of a Cauchy completion and ask us some universal way of adding these higher limits, co-limits type things to any linear two category. And then you can prove that such a thing exists, basically using the same idea as for the one category called proof, where I guess the part where you add direct sum is really exactly the same. There's nothing to say about that. And the part where you actually add the splitting of the two condensation monads is a bit more difficult somehow, because you need to so you want to consider some type of two category whose objects are given by two condensation monads, and then you need to describe what the one morphisms should be, and somehow you end up with some kind of very unusual looking definition of a bimodule. But now, because my thing had the multiplication and the co-multiplication, you have somehow something that's like a bimodule and a co-bimodule in like compatible ways, and it becomes fairly messy fairly fast. But I guess the upshot is this works, it's just a little bit more messy. And now I can tell you a little bit as to why this is actually useful, and something that at least I want to consider and other people want to consider, so hopefully you will want to consider as well. So another definition, but somehow they shouldn't be too scary to an audience consisting of people doing category theory. So a multifusion category is going to be a rigid monoidal finite semisimple category. I know it's a lot of words, but hopefully rigid monoidal is fine by everyone. And by finite semisimple, I only mean it's an object of this two-vector category we saw before. So it's just vect a bunch of times, a bunch of, like, to take a bunch of Cartesian products of vects with itself. So really, somehow the interesting part is in the monoidal structure that you have. And then I just want this monoidal structure to be rigid. And the idea behind these objects is that somehow this generalizes the notion of symmetry in the sense that somehow it categorifies it, and also it also kind of similarly generalizes the notion of a group, which is why people are interested in these objects. And like, unfortunately, the only easy examples I can give you are actually fairly trivial ones, but nonetheless, let me give them to you. So you can consider the category of G-graded vector spaces, but also the category of finite dimensional representations over your favorite finite group. And many other things that come from like a lot of different areas of mathematics. Somehow even analysis is able to produce examples of multifusion categories. So you have something that's rather ubiquitous when even analysts can produce such examples. Another theorem is that somehow this somewhat mysterious Cauchy completion operation of two categories actually induces an equivalence of linear three categories between a three category whose objects are multifusion categories and some three categories whose objects are finite semisimple two categories. Well, now you should probably object and say that I haven't told you what the right-hand side actually means, but I've told you that the Cauchy completion actually makes sense. So it's going to, for me, it's going to be my definition. Just know that there is a way to like intrinsically define for linear two category what it means to be finite semisimple, but I just didn't want to give another definition on top of everything else. And the way this equivalence goes is that you just take your favorite multifusion category, and because it is monoidal, you can view it as a one object two category, and then I just take this Cauchy completion operation, and you end up with something that I want to call a finite semisimple two category. Okay, and let me give you one example, if I can call that an example, but somehow you can take this category of Z2 graded vector spaces and then apply this mysterious procedure, and somehow the way I want to describe the resulting two category is via this diagram. And how should you understand it? Well, the dots represents non-equivalent objects, and then all of the other objects are given by direct sums of those. And then the arrows represents like one morphisms, and then all the other one morphisms can essentially be obtained by like the two different direct sums of these one morphisms. And the thing I wanted to emphasize is that somehow B vec Z2 only has one object by construction, and somehow this picture has two dots, so two non-equivalent objects. So somehow this means that this category B vec Z2 actually has an interesting condensation, two condensation monad living in it. And the way you see it is because you have two dots. Like if you didn't have any interesting thing, you only have one dot. Yeah. And finally, comment as to why you might actually care about all of this. Well, the point is that it's much more convenient to think about E1 algebras, or putting an E1 algebra structure on a two category rather than that putting it on a multifusion category. Why is that? Well, I was purposefully rather vague as to what these three categories actually look like, but somehow the right-hand side really is like a subcategory of the three category of two categories, so something that we understand. But the left-hand side actually isn't. The left-hand side is some kind of like Morita category. Somebody talked a bit about this on Monday, but somehow the point is my objects are like categories with a product, and then I want my one morphisms to be by module categories. So something that has like actions by two categories. That's somehow compatible. And as you can imagine, composing one morphisms in such a three category is just painful. I mean, if you want to do it explicitly, it's extremely painful. Like, of course you can do it because I'm telling you it's a three category, but it's quite difficult to wrap your head around what's actually happening and to actually like do it in practice. So that's why if you want to put a new one structure on something, it's much easier to put a new one structure on a 2 category because that's something we understand, right? That just end up with a monoidal 2 category. Whereas on the left-hand side, it's much less clear what you might end up with. And then going a little bit further, because now I have a new one structure on something that I call the finite semisimple 2 category, I can just ask the resulting monoidal structure to be rigid, and now I have myself a definition of a multifusion 2 category, which is just a categorified notion of the notion of a finite, of a multifusion 1 category. And hopefully, because you're a category theorist, you will believe that if multifusion 1 categories are interesting, multifusion 2 categories are interesting. But it's also true nonetheless, even if you don't believe that just bumping categorical numbers up is something that one should do. They actually have found like genuine applications in topology and algebra recently. Thanks a lot.
Okay, I think we can thank the speaker.